Hey everybody, and welcome to Discrete Math Lecture number 5. Today we're going to talk about logical equivalence, and here's the definition. Two compound statements, U and V, are logically equivalent, and this is how we denote U and V being logically equivalent. It's like an equal sign with an extra bar above it, so instead of 2 parallel lines, we have 3 parallel lines. And if this is a logic statement, then we read this as U is logically equivalent to V. Okay, let's start again. Two compound statements, U and V, are logically equivalent, denoted this way, exactly when U and V have the same set of truth values as displayed in a truth table. So two statements are logically equivalent exactly when they have the same set of truth values as they're displayed in a truth table. So what we're going to do now is look at an example, and an example of two statements that are logically equivalent, and show exactly what we mean when we say they have the same set of truth values as displayed in a truth table. Okay, here is our first example. Show that the statements P if and only if Q and P and Q or not P and Q are logically equivalent. So in order to do this, we're going to create the truth table for each one and then show that they have the same set of truth values on the truth table. So first we'll do P if and only if Q, and that's one whose truth table we pretty much know. We either know the truth table or we know that special case that we remember for an if and only if biconditional statement. We have two simple statements, P and Q, which means that there are 4 possible combinations of truth values for P and Q. Here's how we fill out the table. True, true, false, false. And for the inner statement, we alternate true, false, true, false. There. And this is one of the basic compound statements or compound propositions whose truth values or truth tables we should know. P if and only if Q and I think the best way to do this is to know the special case for the biconditional. And the special case is this. The biconditional is true exactly when what? That's right. Exactly when P and Q have the same truth values. So here they have the same truth values. They're both true. So the statement is true. And here they have the same truth values. Both statements are false. So P implies Q is true. These are the only two cases where the truth values are the same for both statements. So these are the only two cases where the biconditional statement is true. In the other cases, the statement is false. And I'm going to highlight the truth values for P if and only if Q by circling that column. Now we're going to do the same thing for this compound statement. Again, it's made up of the simple statements P and Whoops. But I don't want to write it like that. I want to write my simple statements down first. So I'll write P, Q, and I'll put down the 4 different possible sets of truth values. True, true, false, false, true, false, true, false. Beautiful. So we're off and running. And I guess what I'm going to do, since we need to have the truth values for not P and not Q, what I'm going to do is I'm going to get the truth values for these 2 statements first. So not P, and this is easy. The negation operator just inverts the truth values for P, or switches the truth values for P. It switches true to false, and it switches false to true. Now we'll do the same thing for not Q. The negation operator switches the truth values of Q from true to false, and from false to true, true to false, and from false to true. Next, I guess we need the truth values for this statement, P and Q. This is an and statement or a conjunction. What's the special case that we remember for an and statement or a conjunction? An and statement is true exactly when all of the statements that make it up are true. So we're looking for that special case where both P and Q are true. And where does that happen? It happens right here. So when P and Q are both true, P and Q is true. And that's the only time that it's true. P and Q are never both true simultaneously again. So this is the only case where P and Q are true. We can fill in the rest of the cells of our truth table automatically without really giving it much thought because we know the special case. Now we're going to do the same thing for not P and not Q. And if I'm a really nice guy, I'll probably remove any doubt at all what this negation operator is negating. Although we know this has the highest precedence for any operator. In other words, it negates whatever comes in front of it, and we do that before anything else. But just so that we can remove all doubt, we'll put not P and not Q in its own set of parentheses, just so that we know before we do anything else, we negate P and we negate Q. Now this is an and statement also. So we're looking for that special case where both of these statements are true, where not P is true and not Q is true. And that happens right here. Not P is true, not Q is true. And this is the only time that it happens. So this is the only case in which not P and not Q is true. Every other time this statement is false. Now we're ready to do the whole thing. P and Q, or not P and not Q. And this, in the broadest sense, is an or statement or a disjunction. It's this thing, P and Q, or this thing, not P and not Q. So it's an or statement, this thing or this thing. And what is the special case for an or statement? An or statement is only false when both statements are false. So let's see, when does that happen? It happens here, and it happens here. So right here, both statements are false. And right here, both statements are false. Every other time, this statement is going to be true. So this is the set of truth values for the statement P and Q, or not P and not Q. And look at what we have. The set of truth values for P if and only if Q are exactly the same as the set of truth values for the statement P and Q, or not P and not Q. I'm going to take my answer and I'm going to encapsulate it. Here's my answer. These two statements have the same set of truth values. See, here are the truth values for one. Here are the truth values for the other. So they are logically equivalent. So my answer is in this box, and my work to justify the answer appears in this table and in this table. Okay, a special kind of compound statement that we want to know about is something called a tautology. A compound statement or proposition is a tautology exactly when it is true for every combination of truth values of the simple statements that make it up. So in other words, a compound statement is a tautology when it is always true. Let me show you some simple examples of this. Let's just take the statement P or not P. There are only two possible truth values for P. And this is an or statement, which means that the only time that it's false is when all of the simple statements that make it up are false. Well, in this case, it's not false because P is true. And in this case, it's not, whoops. Let me go back. I didn't fill out the truth table completely. I beg your pardon. Okay, show that this compound statement is a tautology. It's made up of one simple statement. The statement P has two truth values. And we want the truth values for this compound statement. We already have the truth values for P. What I forgot to take into consideration before was that we need the truth values for not P. So here they are. The negation operator just inverts the truth values of P. It switches true to false, and it switches false to true. Okay. Maybe second time is a charm, huh? Now we do the truth values for this statement. P or not P. This is an or statement. What's the special case of an or statement? Isn't it that an or statement can only be false when both of the statements that make it up are false? Does that happen? It doesn't happen here. P is true and not P is false. They're not both false. And it doesn't happen here. P is false, but not P is true. So it's never the case that both of these statements are false, which means that this or statement can never be false. We have a big fat true here and a big fat true here. And this is the set of truth values for the statement P or not P. Let me do it this way. Since the truth values of P or not P are always true, the statement P or not P is a tautology. Here's our answer. Encapsulated in the blue box Here's our answer. Here's our documentation that justifies our answer. Now, that was a trivial example. Let's do one that has a little more meat to it. Okay, I promised a little bit more sophistication. Here it is. Show that this statement is a tautology. And the way we do that is we do the truth table for this statement and show that it's true for all possible combinations of truth values of P and Q. So we take our simple statements P and Q and we write down all of the truth values. On the outside, true, true, false, false. On the inside, true, false, true, false. Now, what should we do first? We have a couple of choices. In order to do the and of these two statements, we have to know the truth values for not P, and we have to know the truth values for P or Q. So we can do either one of these first. Let's do not P. The negation operator just switches the truth values of P from true to false, and from false to true. There, we have not P. Now we need to do P or Q. This is an or statement, a disjunction. What's the special case for an or statement? An or statement is only false when both of the statements that make it up are false. So we're looking for that special case when both P and Q are false. And let's see, I guess this is the only time that it happens. This is the only case where both P and Q are false, and that means the statement P or Q is false only when this happens. Both P and Q are false. All the other times, the statement is true. Now, next, I guess we have to do the conjunction, the and of not P and P or Q. So let's do that. Not P and P or Q. In the most general sense, this is a conjunction. It's the and of this statement, not P, and this statement, P or Q. It's an and statement. What's the special case that we know for an and statement? Isn't it that an and statement is only true when each of the statements that makes it up is true? So in other words, this and statement is only true when both not P and P or Q are true. Does that ever happen? Not P true and P or Q true? Yeah, it happens right here. And this is the only place where it happens. Not P is true, P or Q is true. So the and of those statements is true. Every other time, the and statement is false. Now we're ready to do the whole shebang. not P, and P or Q implies Q. Did I write that correctly? Not P and P or Q implies Q. Okay. In the most general sense, this is an if-then statement, a conditional statement. It's this thing implies that thing. What's the special case for a conditional statement, an if-then statement, an implies statement? Isn't that special case, this statement is only false when we have this thing implying, no, this statement is only false when we have true implying false. Does that happen? Well, this is the only time that this thing is true. When this thing is true, is Q ever false? Let's check. Here's when this whole piece of garbage is true. It's the only time. And when this is true, oh look, Q is also true. So there's never a time when this is true and Q is false, which means that this has to be true for every possible set of truth values of P and Q. So let me circle that, the set of truth values for the statement. The truth values for this statement are always true. So the statement is a tautology. Okay, we'll look at another classic compound statement, the contradiction. A compound statement is a contradiction exactly when it is false for all combinations of truth values of the simple statements that make it up. So in other words, a compound statement is a contradiction when it is always false. Let's look at a very simple example. That we claim that this statement, P and not P, is a contradiction. To verify that, we'll make up the truth table for this statement. And it only has one simple statement. This compound statement is made up of one simple statement, and that's P. And the truth values for P are true and false. And I'm not going to be a dummy this time. I'm going to do the truth values for not P before I try to do the truth values for the whole thing. So here's not P. And the negation operator just switches true to false and false to true. And here's the compound statement that we want to show is a contradiction. It's an and statement. It's this thing and that thing. What's the special case for an and statement or a conjunction? Isn't the special case that an and is only true when both of the statements that make it up are true? Well, let's see. When are P and not P simultaneously true? Well, it doesn't happen here. One's true and one's false. And it doesn't happen here. One's false and the other's true. So it's never the case that this statement and this statement are true simultaneously. One is always true and the other is always false. They're never both true. So this and statement is never true. It's always false. And here's our set of truth values that we circle. My goodness, can we read that? Yeah, I guess we can. The statement is always false, so it's a contradiction. Now let's do one that's a little more complicated. Okay, here's a challenging one. Show that the statement or proposition P if and only if Q and P if and only if not Q is a contradiction. So let's do that. This statement is made up of two simple statements, P and Q. So we fill in their truth values in the truth table. And excuse this notation. It's correct, but it's not what our book uses. There we go. We use this for the negation of Q. So we have P if and only if Q and P if and only if not Q. It looks like the first thing that we're going to have to fill in on this table are the truth values for not Q. The negation operator changes true to false and false to true, true to false, false to true. And next, we have a choice that we can either do this statement or this statement. Let's do P if and only if Q. This is a conditional statement. No, this is a biconditional statement. Each one implies the other. Now, what's the special case for a biconditional statement? Isn't it the case that a biconditional statement is only true when both of the statements that make it up have the same truth value? So whenever P and Q have the same truth value, this statement is true. Well, they have the same truth value here, don't they? So it's true. And let's see, anywhere else? Yeah, they have the same truth values here. So the statement is true here. Everywhere else, the statement is false. Now let's do the truth values for this statement. P if and only if not Q. Oops, I keep wanting to use that notation. And again, this is a biconditional statement. This will be true exactly when both of the statements that make it up have the same truth value. So where do P and not Q have the same truth value? Let's see. Here they have the same truth value. P is true, not Q is true. And here they have the same truth value. P is false, not Q is false. Everywhere else, the truth values for P and not Q are different. So everywhere else, this statement is false. Now I think we have everything filled in. We can do the truth values for this entire statement. P if and only if Q, and P if and only if not Q. This is an and statement. This thing and that thing. What's the special case for an and statement? An and statement is true exactly when all the statements that make it up are true. It's true exactly when this statement is true and this statement is true. So when is P if and only if Q and P if and only if not Q true simultaneously? Not here, not here, not here, not here. This statement and this statement are never true simultaneously, so this statement is always false. This statement is false for all combinations of truth values of P and Q. It's a contradiction. One last compound statement that we want to look at. This is called a contingency. A compound statement is a contingency exactly when it is neither a tautology nor a contradiction. In other words, sometimes it's true, sometimes it's false. It's never always true, it's never always false. Sometimes it's true, sometimes it's false. And we call that a contingency. Now, let's look at some special cases of negations of well-known statements, and also statements involving and or operators together. This is an example that we need to see. The truth table for the negation of an and statement. here's what we're going to do. We're going to do the truth values for P and Q first, and then we're going to negate them. This is an AND statement. What's the special case for an AND statement? An AND statement is only true exactly when both statements that make it up are true. And that happens only once right here. They're both true. Every other time, the statement is false. Now we'll do the truth values for the negation of P and Q. And we just change the true to false. And we change false to true. And we note very carefully their truth values. Now there's something else I'd like to do here before I erase this. I want to do the truth table for another statement. Forgive me, I've modified the original exercise. The original exercise just told us to create the truth table for this statement, the negation of P and Q. But while I was working that out, I thought, it might be a better idea if we revise this exercise so that it says, create the truth table for the statements, plural, the negation of P and Q, which we've done, and the truth table for not P or not Q. Now, I wonder why it is I just have my mind set on doing this also in the same exercise. Call me crazy, but it seemed like a good idea at the time, so let's just go with the flow. To do the truth table for this statement, we'll have to do not P and not Q first. So here's not P, here's not Q. And the negation operator changes true to false and false to true. And it does the same thing when it negates Q. It changes true to false and false to true, true to false, false to true. And now I think we have everything that we need to do this entire statement. So let's go for it. This is an or statement. And what's the special case with an or statement? Isn't the special case that an or statement is only false when all of the statements that make it up are false? So we look for that special case where not P and not Q are false. It happens here. They're both false here. Now, does it happen any other place? Nope, we have false true, true false, true true. This is the only place where not P and not Q are false. So this statement is true for all other combinations of truth values of P and Q. And we'll circle this set of truth values. Now, why was it that I wanted to do the truth table for this thing? in the same exercise as the truth table for that thing? In Southern vernacular, I forget. But maybe it'll come to me. Let's see. Son of a gun. Look at the truth tables here. Look at the truth tables here. They're exactly the same. These two statements have exactly the same truth values. So the negation of P and Q and the negation of P or the negation of Q are logically equivalent. These are exactly the same statements, just in different form. And take a look at this, write it down. We're going to come back to it in about 5 minutes, okay? Okay. This exercise is the analog of the one that we just did. In the exercise that we just did, we negated an and statement. In this exercise, we're going to negate an or statement. And in a related development, we're also going to do the truth table for the conjunction or the and of the negation of P and the negation of Q. I'm just dying to see how this turns out. What do you think is going to happen? Well, let's just plug and chug and see what happens. Here we have an or statement. What's the special case for an or statement? An or statement is only false when both statements that make it up are false. And that happens right here. This is the only time that P or Q is false. It's going to be true all the other times. And then we negate this or statement. So we change true to false, true to false, true to false, and false to true. And we circle this son of a gun to highlight its truth values. Okay, now we're going to do the conjunction or the and of not P and not Q. It's a conjunction, an and statement. What's the special case for an and statement? Isn't the special case that an and statement is only true when both of the statements that make it up are true? Does that happen? Yeah, let's see. Not P is true here and not Q is true here. And this turns out to be the only time when not P and not Q are true. All the other times we have true, false, false, true, false, false. This is the only case where not P and not Q are true. So all of the other times this statement is going to be false. And I take out my red pen and I circle the truth values. And again, in another shocking development, false, 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 true, false, 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 true. These two tables are exactly the same. So here's the point. The negation of an or statement is logically equivalent to the and of each of the two negations. If we negate an or statement, we get the and of the individual negations. Now I'm going to write that down along with the other result, because these are special laws. We should remember them. As a matter of fact, they're so special they have a name. These two logical equivalences are called DeMorgans Laws. The first one tells us what happens when we negate an and statement. When we negate an and statement, we get an or statement that's made up of the negations of the original two simple statements. And the second law is analogous to the first. When we negate an or statement, we get an and statement that joins the negations of the two simple statements that made up the original statement. So the negation of an and is an or, and we negate each of the simple statements. The negation of an or is an and we negate each of the simple statements. These are two laws that we should know. There are a few other cases that we need to look at. The or operator operates on two statements. So if we have three statements joined by two ors, we got to do one of them first. Which one do we do? And the fact of the matter is it doesn't matter. The or operator is what we call associative, which means that we can associate any adjacent pair of statements together first. So we can associate P or Q first, and then associate R. Or we can associate Q and R first, and then associate this pair with P. We're going to get exactly the same thing. And now what about the AND operator? The AND operator acts on two statements. We have three statements here, which means that we have to do one of these before the other. Which one should we do first? And the answer is, it doesn't matter. We can associate any pair of adjacent statements first. So we can associate P and Q first, and then associate this result with R. Or we can associate this pair of statements first, and then apply this AND operator. So it doesn't matter which one we do first. And I guess we call these the associative laws. Now, do we have associative laws in this case? Not really. But we do have something else. Since this statement is in parentheses, we can just do this first and then go P and this thing. And since this statement is in parentheses, we can just do this first and then go P or this thing. And by the way, this is not the way I wanted to write it. There, that's much better. But we can do it a different way. I don't know why we want to, but we could. It turns out that the AND operator distributes over the OR operator. So we'll distribute the P AND to the Q, and we'll distribute the P AND to the R, distribute P AND to the Q, distribute P AND to the R, and we join them with this OR operator. And we do this very much the same way that multiplication would distribute over addition. Think about it. If we have P times Q plus R, that's the same as P times Q plus P times R. It works exactly the same way. And it's also true that the OR operator distributes over the AND operator. So we can take P OR and distribute it to the Q. And we can take P OR and distribute it to the R. And then we can apply the AND operator. These are what we call the distributive laws. There are more laws in the text that are listed. Undoubtedly, a lot more laws than we need to know. I think this will serve our needs very well. If we want to look something up, let's see. I think pages 26 through 28 have all kinds of laws for ands, ors, conditionals, biconditionals. What we've covered so far is plenty.